space after my name. And that's like, it doesn't remove extra space.
Yeah, but for that ladder, Visual Studio, it doesn't recognize the file.
I'll edit out all the
Yeah, it's
right.
really good. So if you run through the terminal.
Okay.
It might be because it's not text, you're not using UTF, like you're not telling it that the contents of the file or the text file.
Make sure you include the file extension as well.
And the whole pattern.
So, are you using any text or any?
We, oh, wait,
So that file's not
Then
in
you can take that and put it in the
Just run that.
oh wow, so you're right.
It says there's no that's that folder.
Okay, so just to check, Kira, do you know when you're going to take the exam?
Next Tuesday.
Tuesday, okay. Presumably after class. Okay. Maria's not here, Danny, Deja, Montserrat, Habibi's, yeah. Okay. All right, and today, what's today's date? 14. Thank you. So, oh, I brought my phone over here. So, today's going to be, it's just going to operate in a rocky manner. I think I'll be able to explain some of it. So, this is problem 354. Find all solutions using Newton's method to 8 decimal places. So we know there are going to be 5 solutions. And to manually use Newton's, well, let's at least understand what that would mean. Let me erase this for the moment. What's Newton's method? Well, we have some formula that says F sub, yeah. Actually, I want this on so the camera can get it. What is it? It's x sub n plus 1 equals f of x sub n plus what? F of x sub n over f prime x sub n. And what is this formula really doing? You have some function, we're looking for a 0. So we have a function goes through 0. And we guess a point that's close, and then we find its derivative and its tangent. Find the tangent line, and we see where the tangent crosses the axis. So hopefully, we start here, and we go here, and then we repeat, and we get closer until we're satisfied. Now, all right, in the case of this guy, I guess I can write it here. So x sub n would be f of x sub n, that would be x to the 5th minus 3x to the 4th minus x cubed minus x squared minus x equals 6 plus, is that right? Do I have that formula right? mislead people. We could spend the time to re-derive it, but that would be repeating. No, I don't give you the formula out here. No. Well, it would have been best to put it on your cheat sheet. Maybe we have to figure it out.
Is it ready?
So, I'm going to figure this out.
First, you said it's supposed to be a minus.
Supposed to be minus? Maybe, yeah. But let's figure it out. So we have some point x, and its value is f of x, right? So we want to know the equation of this line, the kind of problem you've seen on the exam, right? Previous exam. So how do we do that? Well, we know that m, the slope, is the derivative at f of x. And therefore, the equation of this line is what? Y minus f of x equals m times x. X minus x, sorry, x of n times m. That's an equation of a line. What we want to know, so now we have this line, this is the equation. We want to know what it is at y equal 0. So that's negative x of n equals xm minus x of n times m. And x is what we want to solve for. So how do we do that? Well, let's put this on the other side. So we have x of m equals x times m, x of n, m minus f of x of n. Doing this right? And then this is our new x, right? So x equals x of n over m minus f of x of n over m. So our x of n plus 1 is x of n minus f of x of n. But what's m? It's just the derivative of x of n. So whoever said I needed a minus was better memory than I do right now. Okay. So we pick our starting n, we plug it in, we get a new one, and then we repeat. And hopefully what we're doing is we're getting closer and closer to where it's 0. We're doing it numerically, which is really different from trying to solve. I mean, we may be able to find the roots of this, but we might be able to find the roots of this, but what we're doing works no matter what. Well, that's not true. Newton's method could fail too. Remember, we can have this situation where you have something like this, and you pick a poor starting point, and you end up over here, and then you just kind of go back and forth or get worse. that can happen too. So you have to, if you write a program to do this, you have to be careful that that doesn't happen. Okay, so minus, I guess it's +1, this is 10, and minus, you know, the same thing, the same thing over the derivative, which, again, you know, we can figure that out. It's pretty easy. So, I'm pretty sure I put with the instructions that you should go over, find my website. You want to take a look at the you want to look at the code for this. It's called PHP. It's a script language. You computer science guys definitely be worth, you know, just kind of perusing it. The first thing I'm just double checking, see if you gave me any parameters, and here's where I actually do a calculation. It calculates fifth degree equation. PHP, when you're writing for web things, it's kind of weird because you've got what you put on the screen and how to deal with it in the same program. Well, anyway, you can take a look at it if you're interested. But the net result is much more reasonable. I guess I can pull down the screen now. And what are they? 1 minus 3 minus 1 minus 1 minus 1, 6. So we're going to have to plug in some values. This is the coefficients. 1 minus 3. There's 3. Oh, I can see it here. 1, 1, 1, 6. Now, we want it to 8 decimal places. So 1, 2, 3, 4, 5, 6. No. 0. Get that right? 2, 4, 6, 8. Okay. And we have to guess, yes.
The ones after the -3, aren't they supposed to be?
Oh, they're
negative?
negatives. I'm sorry. Thank you. This is why when you're programming and you have a problem, it's always good to have someone look over your shoulder. They probably don't know what you're doing, but just having them there often helps. Okay, so let's pick some kind of big number. Let's say -10. We'll start off on the left, and we'll tell it to calculate. And see if that comes up with anything. Whoa, okay. So the program prints out its attempts after -10, -6, all right. And you can see very quickly here it kind of gets closer and closer. Now what I do in the program is I say, wait until 2 subsequent differences are less than, you know, that accuracy number. So here we have, -1.15 something. So that would be my first guess. At this point, I don't know what that number really is. If it was a nice number like 3, you could go ahead and do synthetic division, and then you could work on a fourth degree. But let's try something. Let's try 0. Let's see what happens. It's my next guess. Oh, that went a lot faster. Okay, so the next number is about 3.36. And let's try another guess. Let's try. If I try 4, I might end up in the same place. But, so I might have to, yeah, I ended up in the same place. So I have to move a little further along. No, that's not good. 6. Huh, keep getting the same. You know, it's possible this doesn't have 5 real solutions. We ought to do a little sanity check here. You could also, you know, it's kind of like cheating, but you could use Desmos to get our initial guesses. Cubed squared minus x plus 6. Oh, well, that's interesting. So what was our first guess was, I forget, about -1? So
No,
that's
-10.
negative. No, that was our, I'm sorry, I guess. What I meant was, what did we,
It's like negative like 1.15 something.
Yeah.
yeah. Okay, so that's this guy over here. I'm wondering why when I put in 0, I didn't get this one. Let's try it again. Or actually, let me try 0.1. And what does it come up with? 3 point. Okay, well now we're getting this one. So how come, let's just put in 1 and see what happens. This just tells you about the foibles of using the Newton's method. It's not always, it will find you a root. Oh, there it is. That's that other root. So this just shows you sometimes your guess has to be good or you can kind of get messed up. I didn't put this in here so much as there's a calculus idea behind it, but certainly for the computer science people, it's useful to kind of see how this works. And for everyone else, you know, technology can be your friend in math. Again, if you see there's some potential issues. I didn't know what else to do with Newton's method. I mean, the book is full of these examples where they give you a little function and you want to iterate 2 or 3 times, and it's just a tedious job that you would never normally do in the real world. You get a computer program to do it for you. Oh, okay, well the next one's a little easier. Use Newton's method. I guess I'll hide this for a moment. Here we want to find the critical points. So, and find the absolute minimum and maximum. So, the derivative is 6x to the 5th minus 6x to the 5th minus 4x cubed plus 9x squared minus 2. So again, it did tell you to use Newton's method, but it's probably worth a quick quick try to use the rational root theorem, which tells me the only possible rational roots are 1, -1, 2, and -2. So 6 minus 4 plus 9 minus 2 is not. Yeah, and plus 1 is not. I'm not even going to try 2. It's the same game. Now, let's say, just for the sake of argument, we don't have a computer. So what would this take? So let's say we have x again. So let's try 0. So I guess we need both, don't we? So f of x is 0, and the derivative is -2. So we use our formula 0 minus, uh-oh, that's not going to work, is it?
Are you solving?
Oh, no, I'm doing the wrong one. Thank you. Thank you. If we want to find this, then we need the second derivative. Thank you. To the fourth minus 12x squared plus 18x. I already know a root. So I can simplify this 30x cubed minus 12x plus 18. And I'm no dummy. I want to simplify it even more. That's 6x, let's see, 5x squared, 5x cubed minus 2x plus 3. All right, so now this is more attractive. So this is the derivative, and this is the function. So if I plug in 0 here, I get -2. And if I plug in 0 here, I get 3. So that means this is x1. So my x2 is now -2 minus -2 over 3. So that's 6 minus 2 is 4/3. Right? So this becomes 4/3. And now I have to repeat this. Yeah, you're going to sit there with your calculator and it's going to be kind of tedious. So that's why I gave you that calculator. Should we go with that?
Yeah, and then can you also explain what the answers were for the first one? I kind of got lost. Like, did we find what they were looking for?
So first the big picture here, which I found on Desmos, which is there are 3 roots. Right? It said find all the roots. So there are 3 roots. And the first one I found by plugging into that calculator -10, and it found this one. And then unless I pick something close to 1, I got this root. Oh, we should check to make sure it's getting the right answers. Maybe I did something wrong here.
The answers need to be to 8 decimal places?
Well, that's what this accuracy thing does. It shows me, it's showing more than 8 decimal places. But you can see, like in this example where I guess 1 and I get that middle root, you can see 1, 2, 3, 4, 5, 6, 7, 8, and then in the 9th decimal place they're different. Just for fun, let's see if it gets more accurate. Like that, there we go. Nope, it's, well, one more iteration. So after 5 iterations, it's accurate to the accuracy that this computer will give us with PHP. I think it's probably a doing floating point. So, so again, if I start at -10, so now I'm getting that first root, and if I said 3. Now I'm getting, 3.36. That's this root over here, 3.365. So, this was an exercise in learning. This is not going to be on an exam, right? This is just, this is how it works. In real world, you might have some complicated function. You might need to find a root. And it might not be, if you have a 7th degree polynomial, you're probably not going to find an easy solution any other way. So, just a little adventure into using computers to do things. So anybody, you want me to continue with that other problem, or you do?
Yes, please.
Okay. So, well,
There's also a part B to it as well.
I'm sorry?
There's a part B to it as well. It's a 2-part problem.
Oh, all right, well, we'll get to that. So, I want to find the roots to the derivative, which is 6x to the 5th. Okay. Can I do this? Just stop it right there. Okay, so first let's just take a look at it. 6x to the 5th. I can't see that far. Minus 4x cubed.
Plus 9x squared minus 2.
Is that it?
No.
Oh, there's an equal in there. Oops. Is that it? No. Man,
To the 3rd.
typing skills. X cubed.
Plus 9x squared.
All
Yeah,
right.
change the sign
Which sign is wrong?
after the x cubed between the 9.
Should be a plus. Okay. So it looks, zoom in a little. So it looks like there are 3 roots. I mean, we don't know what they are. But, all right, let's plug them in here. I'm sorry. 6 minus 4, 9. 6. 0. Minus 4. 9. You got that right?
Yeah.
Wait a minute.
First one should be
6 minus 4, 9, minus 2 is your constant.
It should be 6. It's 1.
I'm sorry?
It's a 5. the top one, x to the fifth should be
Oh,
6.
6, yes, all right. Okay, we good? Calculate, oh, we didn't really. There we go, so what does it come up with? Comes up with 0.507. Ah, no. Yeah, there it is. So that's that root. My guess started at 3, so maybe let's try minus 10 again. So comes up with, you know, more places than they asked for, but negative 1.29. And if we look over here, negative 1.29. And of course, if you guess somewhere in here, hopefully, well, let's try it. Let's try minus 1. That doesn't look good. What happened? He guessed it's 1. Negative 1. He thinks it's negative 1? Is it negative 1? No, it's not. All right. I don't know what happened there. Again, you know, Newton's method is not, you have to put in some code that says, don't go crazy, just don't keep going forever. This looks like negative, let's try negative 0.4. I know this sounds like we're cheating, but. And 44173. 442. So that's how you can use this to find roots. Again, you have to consider that if you guess wrong, you can run into trouble. You could write a program that is a little more sophisticated. You could say start at like negative 10, and then it would just try negative 10, negative 9, negative 8, and gradually try and find all the roots that way. Even that's not a guarantee, but it might be a little more comprehensive. Also, you know, I designed this with something very specific in mind, a polynomial up to degree 5. You could write a program that's smarter, that's up to degree n, or you could write a program that can use other functions like sine, cosine, could do rational functions, if you so choose. And that's kind of directed at the computer side people. Yes?
Do I get extra credit if I write that program? Come on.
I did that once in a class. I made it a project. But I had people work together in groups. I mean, just think of the satisfaction you'll get of doing that on their own. This is not a computer science class, I'm sorry. I'm tempted though, aren't I? Keep trying, you never know what you can get out of the professor. So, we have a topic for today.
Sir, you
Yes.
still haven't done part B.
Oh, I haven't done part B. Oh, darn. All right, what's part B? Find the apps. Oh. Can I just say, you know, we found 3 roots, and you plug them in here? Can I say that?
Sure.
And see which is bigger and which is smaller. Actually, did they put this on an interval? I'll bet they put it on an interval, because if they didn't put it on an interval, I already know the answer. The absolute value is I mean, the maximum and minimums, or infinity and negative infinity. This just grows without limit. Oh, wait a minute, I'm sorry. Take that back. Now, what I said is not true.
It's not on an interval.
Not on an interval. Well, it should be, oh, there should only be a minimum. But we looked at that. Oh, we didn't look at the function. Okay. Let's look at the function. Well, we know. All right, let's just look at the function first. X to the 6. What was the rest of it?
X to the 6 minus x to the 4th plus 3x.
And I'm slow. Minus x to the 4th. Yeah.
Plus 3x cubed minus 2x.
I'm sorry, minus
2x.
2x.
Minus 3x.
Okay, so again, I'm doing a little hand waving here. You can see it has, this is where those 3 zeros of the derivative were, right? So if you plug them in, you're going to find that this is a minimum. It was like more like 1.3 something. So there's an absolute minimum, but of course there's no absolute maximum unless you give me an interval.
It doesn't need a maximum, it just wanted the minimum.
Hmm?
It just wanted the minimum. It didn't need a maximum,
Oh.
it just wanted the minimum.
Oh, all right. That one. I mean, again, you know, you plug each of these in and you're going to see immediately what the value is. Again, I'm kind of hand waving here because it's just plugging into a calculator and figuring it out. That TI-83, like if you plug in the formula and y equals, and you use that calc value function, it's kind of useful for that instead of having to type the whole thing in again. All right. Are we done with this? Okay. I do have a subject for today. Important subject we're gonna do. But I had some thoughts, having started correcting the exam, and because I don't just teach this class rote, you know, here's my notes, here's the problems, here's the lecture. I think about what's going on and try and figure out, well, if I'm not getting through on something to some students, at least one student pretty much aced the exam, so, you know, you could say, well, maybe they knew it beforehand, right? But I'm not getting through to everyone, and I look at the exams and I see the kind of mistakes people make, and I think about it, and I think about why. So, here's an observation. In mathematics, we have something like this. We write a superscript and it means something. differentiation. So when we write this, we know that means e raised to the power of x. But in a way, it's unfortunate. It's historical and it's not going to change. You have to understand this. But it gets in the way. Now let's compare that with something like sine of x. These are both functions of x, but they look really different. Well, okay, we can get that in our heads and inject it. Okay, e to some x and sine of x. The calculator works this way, it shows us what we're doing. But what would really make life easier for us trying to learn the chain rule is if instead of this, we did it the way computer programs do it. Computer programming languages is you have some function exp, or they have one power, and then you type in e, which would be some constant x. And that just says, here it just says, raise e to this x, or here it says raise some various number to the x. Now the reason I say that is, when you have a problem like this, you get used to the idea that, okay, I need the chain rule here, and I have a function within a function. And so this is the cosine of x squared, but then I have to multiply by the derivative here. I think people have that down. But when it comes to this, somehow it just, not everybody, it doesn't flow the way it should. So this is e to the x squared times 2x, right? It would be nice if, at least for this class, we just said, all right, what's t dx of x squared? And then you go, well, derivative of e to the something is e to the something, so it's x squared times 2x. I was thinking about that as I was correcting the exam, and I noticed that when it came to this, a lot of people wrote this. And that's unfortunate because it's not correct. You have to multiply by the derivative of that, negative x, and that's negative 1. So I don't know how to get around that. I mean, we have this notation in math, and it's just really hard. I can't really go ahead and change that. But there you have it. People get confused about this. That brings me to my second observation, that even if this is not a problem for you, maybe the second observation will be helpful. So, I want to talk about a subject that I'm extremely unqualified to talk about for a minute, which is, I'll just say mind, or you can say brain. How does your mind work? How does your brain work? Most people don't really think about it, they just do it, Like here's a bicycle, ride a bicycle. They don't think, how is my mind learning to ride a bicycle? And I run into this concept among athletes and kinesiologists. They talk about muscle memory. Anyone heard of muscle memory? Yeah. Your muscles don't have memory. They really don't. They're just cells that, you know, they do their muscle thing. Muscle memory is in your brain. But we call it muscle memory because after you've ridden a bicycle for a while, you don't notice yourself riding a bicycle. There's kind of, that's not bad. There's this thing that we call the cortex, which as far as we know is where you kind of feel like you are. You see the world, you think. But there's a whole lot of stuff back here in your brainstem that kind of works on automatic. At best, you might observe it going. Like, who here drives a car? Everybody drives? Not everybody, okay. Well, when you learn to drive a car, it's really scary at first because you're there trying to control the thing. But after a while, right, you just get on the road and you're like, oh, where do I get off? Your arms kind of do it themselves, don't they? I mean, you can observe them. You can try and be a little, what's going on with these cars here, be attentive. But it's kind of automatic. And I think where people run into a lot of trouble in math is that there's something that hasn't gotten back here. It's not kind of automatic. Something that, some kind of attention. It's different from driving a car, That it takes a few weeks to kind of get it, the basics. Does anybody here play video games? I play video games. So if you play video games and they're like these 3D shooters, and depending on the game, you might have 3 fingers over here. Well, maybe 4. You put your fingers here, you go left, you go right, you go forward and back. You might do that with your right hand for a while. And then you get some game where you have your mouse over here, you're moving your mouse, and then with the other hand you're doing it. And it typically takes about 2 minutes for you to forget what you're doing. You just get immersed in the game. Because your brain is really good at doing that for physical motion things. It's not good at it for focusing on, math equations and figuring out what to do with them. It's also not that good with numbers, although some of you are probably better than numbers. So how do you train yourself when you're, this is not just about math either. Like every subject you people are studying here needs focus, you need attention, and you need to not be distracted by the trivialities. Like when you see something like this, if you have to kind of back off and go, where's my calculator? You're sunk. You have to look at this and you go, oh, that's 2. It just has to be there. So how do you do that? How do you train? If you're not good at that, how do you train yourself? I'm not really sure. I'm going to make 2 suggestions. One which, if you try it at first, you'll just get frustrated, and then after a while you might get okay at it. And after a while you might even like it and spend a lot of time. But there's a game you can find in the newspapers called Sudoku. Everybody knows what Sudoku is, don't you? Consider finding a Sudoku game and doing it once a day. Right? There are easier ones you can start with that won't frustrate you as much. And then there are hard ones. And just, what does this do? Your mind starts, things in lines. And you spend a little time, and when you're done, here's a little test to see if you're going to do well at computers. When you're all done, if you feel good, you get a little, endorphins are like, oh my God. You're going to be great with computers because computer programs are just like that. You work hard, it's a pain, you're thinking, and then you're like, it works. I'm trying on, oh darn, there's a bug. Feel good about it. The other thing I know of is another game you can also find in the newspapers called Ken. Do people know about Ken? Okay, Ken-Ken's a little like Sudoku in that, you can get 4x4 or 3x3, but the most in the papers will be 6x6. Did I do that right? And part of the rule is the same in that you get the numbers 1 through 6 in each row in each column. But the difference is these will be broken up into, I guess I should use another color. They'll be broken up into sections like this. Some of them they'll give you a number, and then some of them will be weird shaped, and then sometimes like this. And at the upper left-hand corner there'll be an operation like plus or minus or multiply. And the idea is the numbers you fit in here using this operation have to, plus, minus, and there'll be a number. So here, these have to differ by 1. It doesn't matter which goes where. Here, numbers have to multiply up by 3. And so each one of these is a little puzzle by itself. So this is an easy puzzle. Since these all, how do you get 3 into this shape? Well, there's only one way. 3, 1, 1. Nothing else is going to work. You learn some stuff like that. 6 plus can only be 5. Well, that's not true. It could be 5, 1, or it could be 4, 2. So, again, it's a combination of kind of a visual kind of thing, which your brain kind of likes, and then math puzzles. I'm sure there are better ways. But if your mind doesn't kind of like this stuff, and it doesn't like sitting there in a test and probably do this, it's like you don't know how to ride a bicycle, but I'm giving you a bicycle to ride. So you're spending a lot of effort focusing on, turning the handlebars and, turning the wheels. And you're not going to have me for much longer here. We're going to get through this class. Hopefully everybody will make it through. But you're going to have other classes. Most of you are here because you're going to try and do something technical. And you're going to need to deal with equations and numbers and things. So, all right, that's most of what I wanted to say. I wanted to, just before we go on a break, I had one more thing I wanted to mention. And I've had a problem for for quite some time with the idea that this class is I understand why it's a requirement for computer science. They want to see that people can focus in a certain way, but it's not much of what you do here is going to be part of your computer curriculum. And then I found out something which maybe all of you know who are computer science majors, but do you know what the grade you need for this class? Don't believe me, check it yourself. I've heard that what you need, I'm not encouraging you to aim low, what you need is a D minus. I've heard that. Now, check for yourself, because I could be wrong. And don't go for the D minus, go for the A. See how, right? Don't give us, but at least.
Oh, no, it's a C minus if you're a computer science major. This is a C minus if you're a computer science major.
That's what I'm saying. Now, engineers, no. Engineering is either like a C or a C minus or a C plus. And if you're a math major, you better be going for an A. You may not need it, but I was relieved to find the former head of the math department went to bat against the computer science department and said, hey, sure, okay, make sure they can get through this class, but, the curriculum, most of the curriculum is just not required. So why are you, creating this burden? You can be a perfectly good computer programmer without being able to do differential equations or whatever comes next. So, all right, that was it. I'm going to take a break, and then we'll come back, and we're going to have to go a little faster, but we'll get the next section.
You should when you write programs, you should use OS get directory command. They also that scan file path and you scan and go. That's where it's going to open up that file. So when you write programs with other people, you want to use like the get and whatever, and then you want to have that put into a variable and then paste like the main file. Or else it's not going to open. They're going to run it and change it to their directory structure.
Chemistry? Yeah. I don't know what the chemistry department is, Did you fit the data to a curve and then find it, or? Because there's theoretical, you just do like a theoretical model for molecules and come up with an equation at the same kind of field. Yeah. P count, a lot of math. Organic, not so much. But it's important. Even more, you're going to need some physics. The trauma of physics. Well,
It's not a 6 and it's not.
So, gas laws. E equals nRT. Well, there's a statistical model for that from physics. I mean, maybe it could be part of a chemistry, probably part of physics, where you say, all right, we treat atoms as like balls bouncing around and collisions, right? We learn collisions in physics. And then we do some statistics, and we come up with what chemists are interested in, Boltzmann's law. And as it turns out, for quantum mechanics, probably gives you a headache. it intrudes into. Hey, you're in the minority here, I want to acknowledge. You're in a different situation.
Well, today would be.
Math grows on. Maybe. All right, I got
It's no technical.
No, you said it's okay.
It's a movie about Nicholas. You see the previews for that?
I'm not sure because my head is not big here. I was making sure you
No,
said.
I totally see this.
That's all.
You ever see the meme like the monkey sucking like its own walls?
The ones that are set.
That's like the Nicholas Cage. That should have been okay. I watched it too though. It's like could be really. It's probably the first time Nicholas Cage is.
No, I was like watching a video about the bus rider movie.
I still watch like the Nicholas Cage movie. Nicholas Cage loves to go
You watch it, it's pretty good. I should send the movies, yeah, just see
I like going to Saturday.
I think, yeah, me too. As soon as I left, I was like, I was wrong. I was like, while I was doing it, I was like, I know this is wrong. But yeah, it was much
But he's like an A-list actor. Is that movie out? Oh, yeah? Might be able to find it. It would be like one of those goofy like camera ones with the back of the
They got the actor from Narcos in there. They got the actor from Narcos. Okay.
I never watched it.
I'll be right back. He's like the second. Like Nick Cage. And then Pedro Pascal. The actor.
It's out like years like around here.
I don't know. I'm gonna be watching it.
Like early or like old one. I think there's a movie theater like right Henry Hill, right when you get over like
I read the like Conquer.
I think so actually. It won't be something.
Maria.
We
When we were talking about the video, were you the person?
Oh, it's not like after class?
Hmm?
Talking about the video with the one from the
Couldn't hear. The video,
YouTube video
yeah,
with the Vegas and all that jazz?
yeah.
Yeah.
Did you like that?
Yeah, it's pretty cool.
Isn't that cool?
Yeah. Interesting watch it.
It suggests faster than light is not going to happen.
Yeah.
Star Trek aside. Okay.
placeholder.
So, Dobby, were you gonna hand in some corrections? Please do.
TV series, incredibly funny. That Canada. They have a warp drive and there are a bunch of like, genetic memories. Dark matter. You go watch Dark Matter.
Thank you. Yes.
That was a fun movie though.
All right, so, the topic for today is called an antiderivative. And what do I mean by an antiderivative? It's section 4.9 in the book. I already talked a little bit about what the use might be. We're going to talk about that a lot more. But really, I just want to focus on what this is. We've been taking a function, x squared, and finding its derivative. And going in this direction. And now we just want to learn how to go the opposite direction. Now, today we're mostly going to do this mechanically, based on what we already know. So, for example, you already know that the derivative of the sine of x is the cosine of x. So the antiderivative of the cosine of x is going to be the sine of x. But there's a small catch here, which is if this were cosine of x plus some constant, the antiderivative, if this were sine of x plus some constant, the derivative would still be the cosine of x because the constant would go away. So when you go backwards, you have to restore this constant as a possibility, possibly non-zero. Same thing here, antiderivative of 2x is x squared plus some constant. We give that a name that will make sense later in the class. It's called a constant of integration. And sometimes we have a problem where we can figure out what that constant is. Okay. So I talked last week about relativity. I'm not going to do that again. So we're just going to go through all the derivatives that we know and what that tells us about any derivatives. So first let's start with derivative of x to the n is n x to the n minus 1. Well, I give you n x to the n minus 1, of course the antiderivative is x to the n plus that constant, but we're not going to write it that way. We're going to write it this way. What is the antiderivative of x to the n? Well, we want some expression which, when we find its derivative, gives us this. We want a formula, kind of the reverse power rule. Well, how do we figure that out? Well, we know it's going to be the n to the x plus 1 because we want to end up with, the exponent 1 less. But if we found the derivative of this, it would be n plus 1 times x to the n. So we divide this by n plus 1. Right? We find the antiderivative. I'm sorry, put that in the wrong place. We divide this by n plus 1. So if we find the derivative here, we end up with what we want. This solves the problem of finding the antiderivative of some polynomial. All right, we just use this formula here, right? A to the n, x to the n plus 1 over plus 1 plus a to the n plus 1 x to the n over n plus. This will become a 1x squared over 2, and this will just be a0x. But we have that constant of integration. So this is, this is how we would find the, this isn't really a notation, but often when we're talking about a function and we want its antiderivative, we'll describe it, if this is small f, we'll describe this as capital F. So that's how you would do this with a polynomial. The rest of this stuff is kind of just remembering our derivatives and working backwards. So this is f of x. What's our antiderivative? Well, e to the x, that should be pretty easy. We want to venture a guess? Might as well guess now because it's going to be the easiest one. It's going to be e to the x. But, I'm just going to always put this constant in. Right. How about cosine of x? How did we get to the cosine using a derivative? Just got to think backwards.
Taking the sine.
Yeah, it's the sine of x.
When you use the antiderivative, because so you're going backwards, right? So it wouldn't be negative sine x, right? Because you're going in the
Correct.
opposite direction.
Correct. You got to think this, just when you get your antiderivative, you can always check it by finding the derivative. What's the derivative of sine plus c? It's the cosine. I got it right. You just have to think a little. Right now we're doing this purely mechanically. We're going to find it. Why do we want to find the antiderivative? We're going to find out. It's a big item. Right now, I just want to get the mechanics down. All right, how about sine of x? Well, we know it's kind of like the cosine of x, but if I find this derivative, I get the negative sign, so I put in a negative here and it works out. Now, you might think the next thing I'm going to write here is tangent of x, and I'm not. Because we don't know anything that becomes the tangent when we find its derivative. I can write secant squared of x, which I hope
Tangent plus c.
tangent, right? Now, we will learn about how to find the antiderivative of a tangent, but we're just dealing with stuff we know. We know all the stuff on this side. We know how to find its derivative to get here. So we're just kind of writing this stuff down. Secant times the tangent. Anyone remember how we get that?
Cotangent.
No. It's just the secant. I'm sorry, it's the tangent. No, it's the secant. It's the secant. Find the derivative of the secant, it's the secant times the tangent. All right, now here's one. It's going to show up you might not remember the derivative, but now you're going to start having a reason to find the derivative. Anyone think about that for a minute? Where did you see that?
X over the square root of 1 minus x.
Speak up.
The x over the square root of 1 minus x.
No.
Is it the law?
Natural line is
Law.
Anybody really remember?
Is it the law? The law? Law.
I like your guess. No. You're on the right track in that it's what? This is the inverse sine of x. Derivative of the inverse sine, 1 over square root of 1 minus x squared. This one might be a little easier now. What do we call this?
Inverse tangent of x.
Tangent inverse of x. This, it turns out, not this semester, you take Calc 2, turns out to be really useful. Because sometimes you get, you'll have something like this. And we can't really solve this, but we can break this up in something we call partial fractions. There'll be some terms, you know, 1 over x squared or something. And often you end up with this. And you go, aha, inverse tangent. But don't worry about that. That'll come later. All right, just 2 more that also should be quite simple. Should make you happy. Hyperbolic sign. How do we get the hyperbolic sign? By finding a derivative. There's somebody who's an architect in here. Somebody has to be concerned about this. Hyperbolic cosine. How about the hyperbolic? Oh, let's see. How about the hyperbolic cosine? What's that? Yeah. It should be pretty easy. All right. We're almost done with the easy stuff. I want to look at 1 over x. How do we get 1 over? I mean, where was that formula? I guess is x to the n, x to the n plus 1 over n plus 1. So this is x to the minus 1. This formula again works for negative numbers, but wait a minute. N is minus 1, this is 0, that's not going to work. So thank goodness we have something to fill in here. Does anyone remember? What do we find the derivative of and get 1 over x?
The natural law.
Thank you. Excellent. But there's a catch. You see, this is not defined for x less than 0, is it? Or even 0. What happens times if I, I have this function, what does it look like? 1 over x looks like this. And now, I'm trying to figure out, I'm trying to reverse this. Well, perfectly good function here, but the log isn't going to work. Well, it turns out we can just do this. We can just say the log of absolute value of x. If x is always greater than 0, you don't have to worry about this absolute value sign. But clearly, if the derivative of this is going to be 1 over x. So, okay, so that's kind of our toolkit now for antiderivatives. There are some basic tricks that you can use with these. The first one just has to do with constants. If someone says, find the, I don't have notation for it yet. We will. I want to find the antiderivative of, well, let's say 2 times the cosine of x. Well, that's easy. Constants outside, we're outside. It's 2 sine of x. What happens if the constant is inside? Well, you can always work backwards. You can say, well, all right, it's going to be something like the sine of 2x, right? So let's find what the derivative of the sine of 2x is. It's cosine of 2x, good, times, using the chain rule, times 2. So how do I start off here? I mean, how do I end up where I want to be here? Well, I just take 1/2 sine of x, right? If I start off with 1/2, 1/2 times 2 is 1, I end up back where I want to be. So that's the simplest kind of trick we can use for finding antiderivatives. Not all antiderivatives are going to be nice and simple like cosine and sine, but with a constant times the variable, we can kind of work backwards. It's always useful to take a guess, do a guess and check. Let's guess that derivative of the cosine of 2x is the sine of x, sine of 2x. And find its derivative and see how far off we are, and then correct it. Now, we have to be, erase this, we have to be smart about this. We can do a little more. Let's take a look at the antiderivative of x over x squared plus 1. We really have no idea how to deal with that, do we? But we have something here that ends up in the numerator. Kind of like this, right? So we can think of the log for a second. And then we find its derivative. What's the derivative here? It's going to be 1 over x squared plus 1 times the derivative of 2x, of x squared, which is 2x. Well, that looks an awful like what we want. We just add a half, and we've got it. Now there's a little mini lesson here. If you have something which looks like this, f prime of x over f of x, that is, we have a quotient where the numerator is the derivative, or some constant times the derivative of the denominator, then we can use this. We think, well, what's the derivative of f of x, of the log of f of x? It's what? It's 1 over f of x times derivative, exactly what we're looking for. So this is a really useful pattern to find. See if I have an example of it. I think that was an example. All right. All right. Let's look at some other things here. What if I wanted the antiderivative of x minus 1? That looks pretty challenging. But if I write it like this, I guess I should have my, it doesn't sit here, x to the n plus 1 over 1. This is x minus 1 to the 1/2. Maybe our formula will work. That would make it x minus 1 to the 3/2 over 3/2. Well, you might worry about what's underneath here. When we find the derivative of this, we also have to, using the chain rule, find the derivative of this, but that's just 1. So it works. How about square root of x? Oh, that's the same problem. I'm not going to worry about that. That's the same problem. All right. What if we happen to have something that looks like this? Well, you might think, how's this all going to work? This kind of looks like a little bit like the derivative of what's inside here. The derivative of this is 2x, this is just x. So we try this. We try x squared minus 1 to the 5th. Find its derivative, see what we get. We get 5x squared minus 1 to the 4th. That's good. That's what we're looking for. Times 2x. So we end up with 10x, x squared minus 1 to the 4th. That's almost what we're looking for. All we have to do is correct constants. I don't know. The pattern here again is, you see that we've got a function, some number to the 4th, something to the 4th, but we're going to need the chain rule But that's going to work out because we're already multiplying close by what we need. All right, a couple more examples. Am I going too fast? I mean, you got to practice these. You got to kind of get in there and, it's a puzzle. But it's a puzzle, you know how to kind of do the opposite. You know how to check your answer. So you can always go in and check your answer. And if you have to adjust, you have to adjust. If you're really off base, try something else. This is just here to make things look more complicated when they aren't. Let's find an antiderivative here. Well, just as we can do with derivatives, we can separate things separated by a plus or minus into separate problems. So we find antiderivative of e to the x is e to the x. This is 20 times 1 over 1 plus x squared. This is 20 times 1 over 1 plus x squared. So down here we just get 20 times what? Inverse tangent. And I've been a little sloppy. I keep forgetting to this constant. All right, I have one more example for today, and it's just to show you how these. Note that I need two constants, right? I mean, each of these has a constant. You can just combine them. It's just some number. Let's say I have this function, it's a polynomial, 12x squared plus 6x minus 4. And I'm also given this information that will come in useful. That f of 0 equals 4 and f of 1 equals 1. Oh, I'm sorry. This is the second derivative. So I want to find the function, but I have to go through this antiderivative process twice. So, okay, this is 12x cubed over 3, the first derivative, using that formula that I conveniently erased, plus 6x squared over 2 minus 4x plus constant. Which is 4x cubed plus 3x squared minus 4x plus c. Now, I just want to do this again. The function is 4x squared over 2 plus 3x, 4x to the 4th over 2, 3x cubed over this, right? Minus 4x squared over 2 plus c x, I don't know what c is yet, plus d. Or x to the 4th plus x cubed minus 2x squared plus cx plus d. Well, this is where this additional information comes in handy. F of 0 is equal to 4. If I plug in 0, d equals 4. That's nice. Solve that. And if I plug in 1, get 1 plus 1 minus 2 plus c plus 4 equals 1. And I can find out what c is. that's how, when you're doing this antiderivative stuff, and you actually want to find the function, you want to know what the constants are, you need some information. In this case, since we're going back 2 steps, we need 2 pieces of information. So, we will be dealing with antiderivatives till the end of the semester. We're going to do more with them. We can have fun. And there will be a homework assignment. And if anyone still needs to do the exam, I'm going to be down in my office for a few hours now. Anyone wants to come down? Okay. Questions? Here on Tuesday, after class.
Yeah.